Hello everyone listening in the future. I'm Ryan Keeley, a postdoc with the Cosmology group at the Curie Astronomy Space Science Institute. Today I'm going to be telling you about some ways to use model-independent methods in cosmology, particularly about how to reconstruct the expansion history of the universe and how to reconstruct the primordial power spectra. LCDM has emerged as the Concordance model of cosmology. This model explains a number of datasets well, at least individually. In broad strokes, the LCDM model explains well the anisotropies in the cosmic microwave background, how those anisotropies cluster and grow into the observed large-scale structure of the universe, and how the expansion history of the universe accelerates at late times. However, there have emerged a number of tensions between the LCDM parameters inferred by different datasets. Most notably is the so-called H0 tension, which is a 4.4 sigma discrepancy between the present-day expansion rate directly observed from the Cepheid anchoring of supernova distances and that rate inferred from Planck measurements of the cosmic microwave background. Other low redshift distances and anchors, such as strong-length time delay distances and the tip of the red giant branch, also display some tension. There are a number of other tensions involving the growth of structure and other LCDM parameters, such as the curvature or matter density, for example, from the recent KIDS 1000 datasets. Taken together with the H0 tension, these may point towards a discrepancy between high and low redshift physics. While there have emerged a large number of explanations that have reconciled the Planck temperature dataset and the Cepheid dataset, most have not been able to jointly explain every cosmological dataset simultaneously. Notably, explanations that modify the physics at or before recombination tend to fail explaining the polarization datasets or the large-scale structure, while explanations that introduce new physics at lower redshift tend to fail explaining either the BAO distances or the supernova distances. So rather than iterating over through a possibly infinite number of nested extensions to LCDM, even in a hierarchical fashion, or even yet discrete alternative models to LCDM, it can be more fruitful to use model-independent methods to search for a satisfying explanation to the H0 tension. It is in this context that we have to be as agnostic as possible. Our statistical methodology has to be flexible enough to allow for surprises, to allow for unknown unknowns, and thus we must use model-independent or data-driven methods. For cosmology, it is better to use data-driven techniques to reconstruct the distance-redshift relation from the data directly. With the reconstructions in hand, one can then build a model around what the data are trying to say. As Sherlock Holmes might put it, it is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. One of the methods I'm going to be talking about is Gaussian process regression. I've been using it primarily to reconstruct the expansion history of the universe and to test whether cosmological distance datasets are consistent with one another, and also to test whether cosmological distance datasets are jointly consistent with the LCDM model. First, to explain what a Gaussian process is. A Gaussian process, a GP, is an infinite collection of correlated random variables characterized by a covariance function. Where a Gaussian distribution draws a single number, a GP generalizes this concept and draws a function. So in a sense, GP can be thought of as a sampling method, but instead of sampling over a finite dimensional parameter space, such as in MCMC, GP samples an infinite dimensional function space. GPs generally can take an input of what is called a mean function, a function about which the random fluctuations of the Gaussian process varies. Therefore, the draws of a GP can be thought of as hyperfunctions, and thus GP can be used as a method to look for deviations away from this mean function. To test LCDM, then we can choose it as a mean function for our GP inferences. The hyperfunctions phi are related to the expansion history by this equation here, where h sub mf is the expansion history of the mean function. Using GPs to perform a regression utilizes both these understandings of GPs. We essentially take GP as a prior in a Bayesian analysis. In proper Bayesian fashion, we marginalize over the family of hyperfunctions drawn from the GP prior. Each of these hyperfunction samples is then weighted by their likelihood, by how well they fit the data. Histogramming each of these weighted hyperfunctions then allows us to calculate the posterior, not in terms of a set of parameters, but directly in terms of the reconstructed cosmological functions. For instance, the expansion history h of z. We can summarize the methodology up to this point via Bayes' theorem, where the posterior of h of z given the data is the product of the likelihood of the data given the expansion history times the GP prior divided by the evidence. Here we integrate out phi GP, which is the family of hyperfunctions drawn from the GP. From the posterior, we can calculate quantities like the 68 and 95% confidence levels for h of z at any particular redshift. To be concrete about some of the details of Gaussian process, as mentioned previously, a GP is characterized by a covariance function. This covariance function can be quite general, so as long as it satisfies some general properties, like being symmetric and positive semi-definites. We specifically use a squared exponential covariance function with the following form shown here, where evolution variable s of z is just the log of 1 plus z over 1 log of 1 plus z max. And here in these sort of analyses, we take z max to be 3 when we're talking about lower redshift distance datasets. Importantly, the covariance function is characterized by two hyperparameters, sigma f and L. Sigma f determines the heights of the random fluctuations of the Gaussian process, i.e. the scale of the deviations away from the mean function. If the data prefer additional information or flexibility beyond the input mean function, then they will pick out a value for sigma f above 0. L determines the length of the random fluctuations. In simple terms, 1 over L is roughly the number of independent random fluctuations in the range. So Gaussian process samples with large L and large sigma f would have a few large deviations, while small l and small sigma f would have many smaller deviations. Because these hyperparameters encode information about the inferred expansion histories, the hyperparameters must be fit for and cannot be assumed. So it is these hyperparameters that can be used for testing whether the data is consistent with the mean function of the Gaussian process regression. Since sigma f determines the size of the deviations away from the mean function, the test of the consistency of the mean function with the data amounts to testing if sigma f is consistent with 0. So in effect, we calculate the posterior of the hyperparameters sigma f and L and see where the confidence levels end up. So now that we have a general methodology to test whether the mean function of a GP is consistent with the data, we can test if two datasets are jointly consistent with the LCDM model. This is achieved simply by fitting the LCDM model to the two datasets, finding which parameters fit them best, and using the expansion history of that best fit LCDM model as the mean function for the Gaussian process. Thus, if the posterior of sigma f is consistent with 0, then the LCDM model is then said to be consistent with the two datasets jointly. We have demonstrated how these sort of tests work on mock future gravitational standard Siren datasets alongside mock Pantheon supernova datasets, where we're able to detect systematics, whether those systematics were indicative of some cosmology beyond LCDM being true, or biases in redshift estimation. In this figure in particular, we are showing the posterior of GP hyperparameters calculated from mock Pantheon and gravitational wave datasets. Each of these datasets are generated from a CPL cosmology, and the mean function for the GP is taken to be the best fit LCDM cosmology to the two datasets. Thus, we should be able to see a preference for non-zero sigma f if the two datasets are precise enough. And here the posterior is shown with the color corresponding to negative log at the posterior, and the 68, 95, and 99.7 confidence levels are shown in white. Here we do see that sigma f is in fact above 0, indicating that the two datasets are in fact precise enough to detect that the true cosmology in this case was something beyond LCDM. Further, we are currently also using these techniques on the SDSS EBOS BAO dataset and the Pantheon supernova dataset, ultimately showing that the two datasets are consistent with each other and with LCDM. In order to test the mutual consistency of the two datasets, we can choose the mean function for a GP regression of one of the datasets to be a GP reconstruction of the other. Schematically, we start with the best fit LCDM expansion history to, for example, the SDSS BAO dataset, which we use as a mean function for a GP regression of that same dataset. We then use the median GP reconstruction of this BAO from the SDSS EBOS BAO dataset as a mean function for a GP regression of the Pantheon dataset. The hyperparameters inferred from this GP regression will then be able to tell us about the consistency of the two datasets, having made no assumption about the model. And here in this figure, you see the results. You see that the posterior of the hyperparameters are in fact consistent with sigma f equals 0, thus indicating that the two datasets are consistent with each other, basically having made no assumptions about any sort of cosmology. Aside from Gaussian processes and reconstructing the expansion history, we can use other model-independent methods to reconstruct different cosmological functions. Specifically, in another recent work, collaborators and I have used the modified Richardson-Lucy algorithm to reconstruct the primordial power spectrum from the Planck CMB data. The primordial power spectrum is important because it, above all other cosmological observables, contains information about inflationary physics. In general, the power law corresponds to a single-field slow roll inflation case with nearly scale invariant spectra, whereas other non-power law primordial power spectrum would indicate some sort of much stranger inflation with potentially steps or kinks in the potential, or potentially even some sort of large field inflation. So if we are able to reconstruct a novel primordial power spectrum, that would indicate some sort of novel inflationary physics. So the idea with this reconstruction is if we can reconstruct a novel primordial power spectrum that would satisfy both the Planck CMB data as well as the other low redshift expansion history datasets, then we would have reconstructed an inflationary solution to the H0 tension. In general, the observed angular power spectrum of the CMB is a convolution of the radiative transfer kernel, or the transfer function, which incorporates all the information about the background expansion history and the primordial power spectrum. So if we use a radiative transfer kernel with a background expansion history consistent with the low redshift distances, i.e. H0 from shoes, omega matter from kids and supernova, etc., then with this radiative transfer function, the radiative transfer function that results, the modified Richardson-Lucy algorithm then iteratively finds a primordial power spectrum that net yields the same CLs as the best fit Planck power law. To explain a bit more how the MRL algorithm works, we write down the algorithm here, where GLK is the transport kernel, CLD is the data angular power spectrum, CLT is the theoretical angular power spectrum, specifically corresponding to the recovered primordial power spectrum at the ith iteration. So it's important to emphasize that this modified Richardson-Lucy algorithm is an iterative process, and further that it ensures the positivity of the recovered P of k, since GL of k is a positive definite matrix. So the modifications to the original Richardson-Lucy algorithm are specifically this sort of tanh term, which is used to account for uncertainties in the data and to make modifications to the P of k where the data and the theory CLs are the most different. So in the end, when we do apply this algorithm to the Planck data with a high H0 expansion history, we do recover a novel primordial power spectrum. To understand the effects of this primordial power spectrum and why it yields a high value for the Hubble parameter, we must first understand what effect changing the Hubble parameter would have when fixing the primordial power spectrum to the best fit Planck power law. Just shifting H0 induces a purely geometric modification to the CMB's CLs by changing the inferred angular diameter distance to the surface of last scattering. This in turn generates a phase shift in the CLs that is consistent across the acoustic peaks, so in effect, the MRL deconvolution is generating a primordial power spectrum that de-phase shifts the CLs. The effect relative to the best fit lambda CDM model of changing H0, changing the primordial power spectrum and changing both, are shown here in this figure. The figure shows plots of CLs for a power law lambda CDM model with an H0 of 73.5 in blue, an MRL model with H0 of 67.8 in orange, and a model with an MRL model of H0 with 73.5 in green. And these are all plotted relative to the best fit power law lambda CDM model with H0 of 67. So the two different modifications shown here in green, again, induce basically equal and opposite changes to the CLs. And so when they're combined, they induce basically no change. The reconstruction itself is basically only exploring 2 points in a parameter space, so we want to generalize it. To do so, we take the reconstructed primordial power spectrum from the MRL algorithm and the best fit power law primordial power spectrum from the lambda CDM model and interpolate between them. We can do this while varying the background parameters as well. In total, we essentially have the same six parameters of the base lambda CDM model with one additional parameter f, which characterizes the deviation towards the MRL template. We call this in total the deformation model. In the figure here, we simply display a few instances of the deformed MRL-derived primordial power spectrum, where f equals 0 is the MRL primordial power spectrum in blue, and f equals 1 is the best fit power law primordial power spectrum in yellow. So the main result of our work is to perform a Bayesian model selection between lambda CDM and this deformation model. First, we calculate the posteriors for the parameters of the deformation model using only the TT dataset from Planck. This is to show that independent of the Cepheid H0 measurement, the deformation model can predict H0 values higher than LCDM. Then, when the Cepheid H0 constraint is included, we show that the resulting parameter space is actually a good fit to both datasets, thus resolving the tension. In this figure, we show that the results for our deformation model, for the TT dataset alone, the best fit parameters of the deformation model are H0 is equal to 70 plus or minus 1.2, and F is equal to 0.64. These best fit parameters yield a likelihood better, actually, than the best fit LCDM model, with a delta log likelihood of around 2.5. This is intriguing since even on its own, the deformation model can explain the temperature anisotropes in the CMB better than the LCDM model, while also predicting higher values of H0. In total, we calculated a base factor for the two models for the TT dataset of log k of 2.2. Then, when we combine the Planck dataset with the Cepheid H0 measurement from Reese et al., the best fit parameters shift to H0 is equal to 71.8 plus or minus 0.9, and F is equal to 0.39 plus or minus 0.16. And the base factor for this case is the log of k of 5.7, which according to the Jeffreys scale amounts to strong evidence. Part of the discussion around this model must include the fact that the MRL reconstructed primordial power spectrum is non-trivial, and hence either potentially overfit or a priori unlikely. Saying that this primordial power spectrum is overfit is similar to saying that the MRL deconvolution used to describe was just fitting noise in the Planck 2015 data. However, when this primordial power spectrum survived new additions to the dataset and changes to the modeling of foreground and systematics to also explain the 2018 data, that this primordial power spectrum has a well-defined observable effect on the CLs further sort of contradicts the idea that this result is just noise. Expressed in another way, one might reasonably believe that the numerous non-trivial features in this primordial power spectrum are a priori unlikely. Such concerns are understandable, but such subjective prior belief is nothing to build a firm conclusion on. Such a priori preference for a featureless primordial power spectrum basically lasts only until someone writes down an inflationary potential that predicts the features derived in the deconvolution. So we do not seek to rule out ideas solely on a priori arguments. So now we seek to answer the question of what features in the MRL reconstructed primordial power spectrum are primarily driving the preference for parameter values that are different from those inferred from LCDM. One potential way to answer this question is to apply various smoothings, filters, or wavelength transforms to the MRL reconstructed primordial power spectrum and check if the resulting primordial power spectrum can achieve the same likelihood. Even simple techniques like frequency cuts and low-pass filters suppress the features in the range of k around 10 to the negative 4 to 10 to the negative 2, leaving only the sinusoidal oscillations at high wave number. To test the effects of the filter, we scanned over a cutoff frequency of the low-pass filter and calculated how much the likelihood change. For larger values of the cutoff frequency, the change in the primordial power spectrum is small. When scanning over the cutoff frequency, we found no preference for any filtering, but some amount was still allowed. Applying a cutoff frequency of 0.6 megaparsecs to the MRL primordial power spectrum, the likelihood is marginally worse by around a delta log likelihood of 0.5, where the jackiness and the high wave number part of the MRL PPS is removed. The constant likelihood basically biases a priori subjective belief. Further, all the low wave number features are also removed. To more precisely answer the question of which features give rise to the MRL preference for a high H0, we also tested a case where the low-pass filter was applied to only the features above k of 0.25. This choice was motivated by the fact that above 0.25, the only meaningful effect on the CLs was for L values above 2500, which is a regime that is basically unprobed by CMB observations. Keeping with these expectations, we find that essentially all of the features above k of 0.25 can be filtered away and maintain the same likelihood. We show this high k filtering case in the figure, where in green we show the filtered part of the PPS, the blue MRL and the green filtered curves combine to form the tested primordial power spectrum. Thus, it is apparent that these mid-wave numbers, 0.01 less than k to k less than 0.025, these oscillations are what compensate for the phase shift in the acoustic peaks coming from different background parameters. It is not unreasonable that these features could arise from steps or kinks in a physical inflationary potential, such as wiggly-whipped inflation. Thus, these sort of deformed or filtered primordial power spectrums offer a new hope that inflationary physics beyond the simplest single-field slow-roll inflation might be true. This brings us to the conclusions, where I just want to emphasize the power of model-independent methods for explaining the H-naught tension, since they can give us surprising results. Thank you for your attention and for your time, and thanks.